6. Remember, that's the section. Well, first of all, does anybody have any questions I want to go over? No, everybody good? All right, well, let me know if you do. Today we're going to go over 4.6. I did want to let you know that the homework is, oh, never mind, I changed it on there. My paper said 37, so I want it 31 through 35 odd. So this is graphs of other trigonometric functions. We talked a little bit about, or we talked a lot about 4.5, which is the graph of the sine and cosine curve. And so I want to talk about what the graph of all of the other trig functions look like. Okay, so and the reason we skipped this on Monday is because it's way easier to do online where you can see it. And that version of Desmos is not going to help us. So let's go back to here. So just to kind of remind ourselves, let's graph a sine and cosine curve. Okay, sine of x, y equals the cosine of x. Okay, if you ever graph something on Desmos or on your, this especially happens a lot on your TI calculator, and it looks kind of crazy, it might be because your calculator has two modes. One is in radians and one is in degrees. So you'll see if I switch to degrees for some reason in here, my graph looks like this is not a sine curve. And that's because it's going to go from 0 to 180. So I have to, well, no, it's not even going to do that. I think if I set it right, let's see. X goes from negative 200, not 2000. Oh, to 200. Let's see if I can set it up so that it works nicely. I don't even know if your calculator, oh yeah, there we go. So if I set it to degrees, I can make it work, right? Because your sine curve is between 0 and 360 degrees. I don't know why I even did 180. 0 and 360 degrees, right? Or you can go ahead and switch back to radians, which is probably the easier one because that's what we mostly deal with. And look, when I switch to radians, it like really makes it crazy. So let's go back to a nice yikes. Okay. So basically, you want to be in radians when you start, or else you have to mess with all the stuff that I'm messing with now. I just proved my point that that's totally why I did that, right? I don't know how to reset it to the beginning. 3 and 3 and negative 3. I don't know. Okay, well, it's still not perfect, but you get the idea. Let me reset this a little bit. So don't mess with it. Right? Or set it back to standard. All right, that's a little bit better. There's my sine curves on my radians. All right, so all that to say that we already studied all this, but what we're going to talk about today is we're going to talk about what happens when we graph tangent, cosecant, secant, and cotangent. What does that look like? Okay, so first of all, I want to just think about if we can think what would the graph of the tangent be if we didn't even just plug it into our calculator. So what I want to remind you is that the tangent of x is equal to the sine of x over the cosine of x. Okay, so for example, right here, if x equals 0, right, the sine is 0 and the cosine is 1, so 0 over 1 would be 0. So the tangent of 0 is right there. Okay, if I go up here to this point, at this point, which is at pi over 2, by the way, this is at pi over 2. At pi pi over 2, the sine is 1 and the cosine is 0. And can we ever do 1 over 0? Are we allowed to divide by 0? Not allowed to do that, right? So this point right here is actually an asymptote of the tangent function. Okay, and then the tangent curve is just a ratio that goes in between these two values, and it looks something like this, because here we have another asymptote of our equation. So I think we talked about this a couple calls ago, maybe 2 weeks ago, but I just wanted to tell you that's why the tangent curve doesn't look like the sine or the cosine curve. It's a ratio of the sine to the cosine curve, so it actually has some asymptotes. So if I go and graph, I'm actually just going to start over here. Leave Desmos. Oops, sorry. Start graphing. All right, there we go. Y equals the sine of x. Y equals the cosine of x. And y equals the tangent of x. So look at that crazy tangent curve. All right, the tangent curve looks like this because if we zoom in here at this value where we get our asymptote is pi over 2, right? And so at this value, what it's doing is it's taking 1 divided by 0, and we're not allowed to divide by 0, so that's why you get an asymptote right along here. Okay, also over here, you're going to have -1 divided by 0, so you get another asymptote of the graph. So that's why the tangent curve doesn't look like the sine or the cosine curve, because it's a ratio of the two, and you get those two asymptotes. Okay? Does that make sense? Ish. You're like, okay, tangent curve's kind of crazy, right? So let's talk about just the sine curve. Let's go back to just the sine curve. Here is one period of the sine curve, right, from 0 to 2 pi. So what do you think happens when I graph the reciprocal function, which is the cosecant of x? What do you think that's going to look like? So the cosecant of x is the reciprocal. So that means the cosecant is 1 over the sine. Okay, so right here, this is the easy one, right? If the sine of pi over 2 is 1, 1 over the sine, or 1 over the sine of pi over 2 is going to also be 1, right? Because the reciprocals are opposite each other. Okay. We also get some asymptotes, right? Because what happens here? When you take the sine of 0, it's 0. And when you take the reciprocal of 0, 1 over 0, you can't do that. So you get an asymptote. Okay. Again, here, the sine of pi is 0. So if I take the cosecant of pi, it's going to be 1 over 0, and you're going to get an asymptote again. Okay, so that's the sine and the cosecant. Remember, those are the reciprocal functions of each other. Okay, what do you think is going to happen if we do the cosine and the secant? So we get the same kind of curves, right? The cosine has these values where it's equal to 0. So wherever those values are, when you go to take the reciprocal is going to be 1 over 0, which is not possible. So it's going to be an asymptote. Okay, and then the last one I want to show you is our tangent curve. Remember, our tangent curve looks kind of crazy, right? And then our cotangent curves are cot. Sarah would really like this. Our cotangent curves, here I'll turn, there's their tangent. and your cotangent curves are the reciprocal versions of those. So it makes a pretty crazy looking graph when you put all those on there. So the first part of your homework is just matching the graphs to the functions. And then through 23, it says sketch the graph of the function, include 2 full periods, use a graphing utility. So I want you to not sketch it by hand. I want you to just graph these and kind of see what they look like. So for example, number 6 is y equals 1/4 the tangent of x. So our original curve, I would just, these are basically just graph them and kind of see how you think things are going to react. So I'm in section 4.6. Y equals the 1/4 of the tangent of x. So what happens to your tangent curve if you make an amplitude of 1/4? Kind of like dampens your tangent curve, right? What happens if you put a 4 inside of your equation? You get a lot more tangent curves more quickly coming. Okay, what happens if you put, oops, that's not what I was trying to do. Oh, that's crazy, right? What happens if you multiply your tangent by, I'm trying to do something here, by 14, it goes crazy. 1/4, that's what I was trying to do, 1/4 of x. Then you get tangent curves that are occurring less frequently. Okay. So this is just really a function of just graphing it for 1 through 23. Okay, and then 31 through 35, I do want to do a quick example for that. So I just want you to be aware. It says, use a graph of the function to approximate the solution to the equation on the interval from negative pi to negative 2 pi to 2 pi. So they want to know what are the solutions of the cotangent of x equals negative square root of 3. So this looks complicated, but think about this. This is back to like graphing can basically always help you solve equations, right? You always put on one side of your equation, you put the left-hand side. So the cotangent of x, right? And we want to know where does that equal? Y equals negative square root of 3. Sorry, I can't see my square root of 3. Okay, and we want to know what are all the values that make this true. And it says approximate the solutions to the equations between negative 2 pi and pi. Okay, so what are all the solutions that make this true? Well, x could be equal to negative pi divided by 6, or 5 pi divided by 6, right? 11 pi divided by 6 is, oh, it's also a solution, right? That's also less than 2 pi. So all 3 of those are solutions where x, if you put in x equals negative pi over 6, x equals 5 pi over 6, or x equals 11 pi over 6, you'll get negative square root of 3. So I just want to show you can solve these kinds of equations. It's not too difficult to do, right? All right, how'd you guys feel about that? Kind of wild, but you get it. I like it, Greta. Okay. So now we are on to section 4.7. Okay, so 4.7, remember we introduced the idea of the inverse trig functions. So remember, these are different than the reciprocal trig functions that I wanted to call inverse trig functions before, right? So let's look at these on a graph just so you can visualize them all. Again, we have our sine curve, right? We have our reciprocal function, which is the cosecant curve, right? And then we also have our inverse sine curve, or also called the arc sine. So that's actually underneath your functions under trig. There's sine, and then right next to it, you see the inverse sine of x. Okay, so you can see that all three of these are different functions. They look a little bit different, right? Sine is just basically, so another way, well, I should have said this before. If I do 1 divided by the sine of x. Okay, let me move this up here. Before we even get to this inverse trig function, let me just double check you guys understand. On the sine and the cosecant is the reciprocal, which just basically means 1 over the sine. So you can see if I graph the cosecant and 1 over the sine, they're the same curves. So that's all that the cosecant is. It's just 1 over the sine. Okay. The reciprocal function is the one that looks like this. Okay, so you can see that it's this funny little curve here. And remember, our reciprocals always reflect across y equals x. So you can see how these reflect across y equals x if you graph it. Right, pretty cool. What's interesting about the inverse sine function is that it's only valid from, oh, where's our paper? The range only goes from negative pi over 2 to pi over 2. Okay, so if I go back to here, the range only goes from negative pi over 2 to pi over 2. Any values beyond that, we have to actually kind of do some finagling to make it work. Okay. So does that graphically kind of help distinguish between the sine, the cosecant, and the inverse sine? What those are? Sorta. You're like, why? All right, so I think it kind of helps visually. So what this actually does, why are we learning this, and why are we learning all these functions, right? So for example, if you had a problem where you had that the sine of x equals, I don't know, 50, okay? And I wanted you to solve for x for me, right? We have two tools. We have the cosecant, right? But does the cosecant actually do anything in terms of solving this equation? It doesn't, because reciprocals, like, you can't multiply by the cosecant to get rid of the sine. That actually doesn't work in this case. It doesn't work with trig. Okay. In order to get x by itself, what you have to do is use the inverse function. So if I take the inverse sine of the sine of x, these two, the inverse basically undoes the sine function, and you're left over with x. All right. But if I take the inverse sine of one side, then I have to also take the inverse sine of the other side. And this is a value that I can calculate either with a unit circle or a graphing calculator to find the value. So the inverse sine is actually really powerful in solving equations. and doing that, okay? Does that make sense? Are you guys still with me? All right, cool. So let's do some examples. Oh yeah, and by definition, right? Those are the inverses of each other. So we did a couple examples on Monday, I think of 1 through 9. So let's do from 3 through 19. Let's do a couple examples in there. Okay. All right, I'm just looking here which one we want to do. Let's look at number 14 here. It says, in exercise 14, determine the missing coordinates of the points on the graph of the function. Okay, so let me open this up on the clipboard. Maybe. I don't know what I just did. Try again. Maybe I picked something else. There we go. Okay, so it says, find the missing coordinates of the graph, and you'll see that this is a graph of the arc cosine of x. Okay, and so what they want me to do is to find the values that are on this graph. And how I'm going to do that is I'm going to use my unit circle. So I have a unit circle up here that I'm also going to take my unit circle and put it on here. Over here. Not on top of it. Over here. Oh, make it littler. It's taking over the world. No, not that. All right, let's try again. There we go. Now we have enough room for everybody. Okay, so first of all, let's talk about this. This is a graph of the arc cosine curve. Okay, and so remember that the arc cosine, if you go back to your notes, okay, the arc cosine is only true when y is between 0 and pi. Right, so that's important because if you look at your unit circle, the arc cosine is only valid when y is between y is between 0 and pi. So basically, it's only true on the top half of your graph. So basically, everything down here you can't use for arc cosine or inverse cosine. You're only allowed to use the top part of your unit circle for that. Okay. So let's think about this. Which one do I want to start with? I want to start with this value up here. All right. So if I were to take, well, let me explain this. The arc cosine of x is my function, right? And that has a relationship. Sorry, I'm just trying to think of the best way to explain this without being totally confusing. So if the arc cosine of x equals y, right, that is the same as saying that the cosine of y equals x. Okay, this is the definition of what the arc cosine or the inverse cosine is. And you'll actually find this in your notes too. Right here, right? Y equals the arc cosine of x if and only if cosine of y equals x. Okay, so we have this function graphed for us, and we need to figure out what the values are. Okay, so the first one is, what happens when x equals 1/2? Okay, so we want to know the arc cosine or the inverse cosine of 1/2 equals y, right? Another way we could write this is we could say, well, when does the cosine of y equal negative 1/2? Because negative 1/2 is our x. So if I look at my graph, okay, remember your cosine is always your x value. So where is there an x value of 1/2? Right here, right? So if I take the cosine of 2 pi over 3, the cosine of 2 pi over 3, that equals 1/2. Are you guys okay with that? I'm just looking at my unit circle. If I take the cosine of 2 pi over 3, it equals 1/2. Right? So that means by definition that the inverse or arc cosine of negative 1/2 is 2 pi over 3 because they have this inverse property. Okay, so this point right here would be at 2 pi over 3. I know it's heavy stuff, right? So let me do the next one. If I didn't make a total mess on here, let's see. I'm going to leave this up on here so you don't have to see me rewrite it here. Well, I can erase that bottom part for this cosine. All right, so now in purple, yes, purple. Okay, I want to know over here, I can't write today. I want to know over here what happens, what is this coordinate? So this is some x at pi over 6. Okay, so this says I can use either one of these things, and I have a y term, right? So what is the cosine of pi over 6? What does that equal to? Well, the cosine of pi over 6, remember, is I look right here, and I look at my x term. The cosine of pi over 6 is square root of 3 over 2. Okay, so that means that my coordinate right here is the square root of 3 over 2. Okay. And then the last one that I have to do is right here. What happens when x equals negative 1? What is my y? When x equals negative 1, basically I'm trying to figure out, well, when is the cosine of y equal to negative 1? Remember, your cosine is your x value, so the cosine of pi equals negative 1. So that means that the arc cosine of -1 equals pi. So the solution for this one would be pi. Okay. I know it's a little weird, but I think as you try it, you'll get used to it. Okay, so that's 13. 15 through 19, it says use a calculator to approximate the value of the expression. Round your answer to the nearest hundredth. So you guys can definitely do this, right? I just want to note that, Desmos, that's what I'm looking for. Make sure that your calculator is on radians when you do this again, because those values are in radians. So for example, number 16 says, find the inverse sine of 0.56. So basically all you're going to do is you're going to take the inverse sine of 0.56, and you find that that value is, so it's to the nearest hundredth, right? So it would be 0.59. Okay, so now we're going to get to, this is the last part for today. And then on Monday, we're going to actually finish this chapter with an easy section, 4.8. So this is like the hardest stuff. Okay. Here we go. So 29 through 53. Actually, 29 through 45 are the tricky ones. After that, you get to use your calculator again. Okay, it says use the properties of inverse functions to find the exact value of the expression. All right, so the first few actually are really easy. So if you take the tangent of the arctangent, that's basically taking the tangent of the inverse tangent. This is actually just going to be equal to the value. It's just going to be equal to 35. Yay, that's easy, right? If I take the sine of the arcsine of -0.1, that's just going to be equal to -0.1. You're like, all right, Mrs. Ross, this is not hard, right? Why are you doing this? Let's get to number, let me skip down a couple. What if I want to take number 38? I want to take the inverse cosine of the cosine of 3 pi over 2. So you may be really tempted to just say, oh, well, she's saying that if I take, the inverse of the trig function, it will just equal whatever value is in there. But this does not equal 3 pi over 2, unfortunately. Bum, bum, bum. Because when we're talking about the sine, cosine, and tangent, we have a very specific set of values that it's valid over. And I honestly don't even know if Desmos will do this or not. So I'm going to give it a try. But I think, I don't know. Let's see here. Let's see what Desmos does with the inverse cosine of the cosine of 3 pi over 2. Inverse cosine of the cosine of 3 pi divided by 2. Okay, so it does evaluate it, but it's not oh no, wait, this one might be okay. I might have picked one that was okay. Hold on a second. I picked one that was okay. Hold on a second. This is where it gets a little bit complicated. Obviously, as I'm explaining it, it's a little bit complicated to explain it. So let me pull this up again. All right, so let's talk about number 38 and what this means. Okay. Or let's even talk about, well, yeah, let's do this. Okay. If I wanted you to find the inverse cosine of the cosine of pi over 4. Okay. Let's do what's in the parentheses first. What is the cosine of pi over 4? So the cosine of pi over 4 is the square root of 2 over 2. Okay, and then if I take the inverse cosine of the square root of 2 over 2, that basically means find the square root of 2 over 2 and tell me where it is on my unit circle, and that will be equal to pi over 4. So you can see that when you take the inverse cosine of the cosine, it equals pi over 4. So it's basically like, oh, I just take this value and then I plop it in there and all is good, right? What happens though is that when we, just look in here. Yeah. So does this make sense, Mackenzie and Greta? Does it make sense how, I guess, how to even find that inverse cosine? So for example, if I've asked you to find the inverse cosine of oh, hold on. If I asked you to find the inverse cosine of negative square root of 3 over 2, could you tell me what that would be? That's a 2. All right, Greta texted me. Let's see. It makes enough sense, you guess. You crack me up, Greta. So if I asked you to find the inverse cosine of negative square root of 3 over 2, what you do, since you're finding the inverse, is you go and you find where is negative square root of 3 over 2. Oh, that is at 5 pi over 6. So the inverse cosine of negative square root of 3 over 2 is 5 pi over 2. Okay? So that's how you find the inverse function. So what I was getting at, which I kind of stepped ahead a couple spots, so I apologize for that, is when I get to number 38, you might be really tempted to say that the answer to number 38, as I'm cleaning up here, is 3 pi over 2, which it is not. All right, so the answer to number 38 is not 3 pi over 2, and I will explain why, even though I just kind of showed you that it always looks like that. So what is, if I just take the inside of my parentheses, what is the cosine of 3 pi over 2? The cosine of 3 pi over 2 is 0, right? The cosine of 3 pi over 2 is 0, because if I look at 3 pi over 2 and I look at my x value, which is my cosine, then I know that the answer is 0. Okay, then what is the inverse cosine of 0? Because this is what's inside here is equal to 0. What is the inverse cosine of 0? Okay, So what you have to remember is that the cosine is actually only valid up here. The cosine's only actually valid up there, right? So what I want to do when I find the inverse function is I want to find where does x equal 0? Well, it equals 0 up here at pi over 2. So the inverse cosine of the cosine of 3 pi over 2 isn't 3 pi over 2, it's just at pi over 2. Okay, and that's why when you went to Desmos and you plugged it in, or I plugged it in, not you. When I plugged it into Desmos, right? My answer of the inverse cosine of the cosine of 3 pi over 2 is 1.57, which happens to be pi divided by 2, not 3 pi over 2. Okay. So let's do another one. Let's do number 36. Okay, so let's get rid of all this stuff. That's going to take too long. Let's do number 36. So 36 says the inverse sine, grab my pen, the inverse sine of the sine of 7 pi over 4. So we have the inverse sine of the sine of 7 pi divided by 4. So the first thing we need to do is what's inside the parentheses. What is the sine of 7 pi over 4? Okay, well, the sine of 7 pi over 4 is down here, and it is your y value, right? Your cosine is your x value, your sine is your y value. So the sine of 7 pi over 4 is negative square root of 2 over 2. So then what is the inverse sine of negative square root of 2 over 2? So this is where it gets a little bit tricky. You might be tempted to say that it's right here and it's 7 pi over 4. But that's not actually valid as one of your solutions, because if you go back to your notes, you'll see that the sign is only valid between negative pi over 2 and positive pi over 2. So we have to flip our thinking a little bit and know that the sign only goes on this side over here. This side's out, right? This is pi over 2, and we need to think about going this way as going to negative pi over 2. So this value here is not going to be at 7 pi over 4. Instead, we're going to call that at negative pi over 4 because it's at the same position as this. So the inverse sine of negative square root of 2 over 2 is actually negative pi over 4. So you kind of have to play this game when you're taking inverse sines of, is my answer in the right range of what it should be? So then again, if you would type this into a calculator, right, the inverse sine, let's see if it'll let me do this, the inverse sine of the sine of 7 pi divided by 4 is negative 0.785. So that's not 7 pi divided by 4, right? That's a big number. It is negative pi over 4. So it's kind of like this game of figuring out what is it? And then where does it land on my graph? All right, so how do you guys feel about that? Slightly confused, but feel like maybe you could try it? It's doable, I know. The thing is, you can actually check if you did it right at the end by kind of plugging in a value. So if we want to on Monday, we can do a few more examples. And then, like I said, on Monday, we're going to wrap up 4.8. So kind of keep that in your head that we'll be finishing up. 4.8, I feel like, is easier. It's more common sense. It's applications and models. So I actually feel like that's a lot easier than this. This is probably the hardest that we get in trig. So thank you, ladies, for coming today. And let me know if you have any questions, and I'll see you guys on Monday. Bye, guys. Yeah, have a good week, too.